Prepare for trouble.
and make it quadruple.
To solve the problem of trajectory prediction.
Using visual features and recurrence relations.
Poojita.
Pranav.
Kunal.
Anurag. Team Rocket blasts off at the speed of light. Surrender now or prepare to fight. Now that we've seen from that short animation how our various approaches perform against the task of trajectory prediction, let us define the problem more concretely. Trajectory prediction involves predicting the future locations of an agent, such as a person or vehicle, being given their location history. Several approaches have been adopted in the past, some of which treat this as a pure sequence prediction problem, while others also incorporate visual features from the video frames. More concretely, we ask two research questions. Does social interaction play a role in human trajectory prediction, with the intuition that humans often rely on the trajectories of others in their vicinity while planning their own trajectories? And the second research question, does incorporating visual features help in predicting better trajectories? We perform our analyses on two datasets. The first is a real-world dataset called the BB Hotel dataset, and the second is a forking paths dataset, which is a simulated dataset shown below, and allows us to extract scene features more easily than the BB dataset, thus allowing us to exploit the second modality of vision. We first build a strong baseline model, which is a simple LSTM model that takes in the X and Y coordinates of an agent and predicts the future X and Y coordinates. Our analysis shows that our improved architecture, which is a 3-layer stacked BLSTM model, performs the best on the evaluation metric average displacement error. Note that there is a huge difference in the error between the BB dataset and the forking paths dataset, and we attribute this to the shorter length of sequences in the forking paths dataset. To answer our first research question, we re-implement the social LSTM model, which has a novel pooling mechanism which pulls together the hidden state representations of different pedestrians which are in a predefined vicinity of each other. To answer our second research question, we extract scene features from the forking paths dataset using the annotated bounding boxes and pass these scene features through two new architectures, the conv LSTM and the convolution plus LSTM sequential model. The conv LSTM model is similar to an LSTM model, except that all the matrix operations inside an LSTM cell are replaced with convolution operations. The convolution LSTM model first passes the input image through a convolution neural network, and then passes the flattened representation through an LSTM, uses this output to predict X and Y coordinates. On this slide, we summarize all our results and find that the convolution and LSTM model performs the best, while both models that incorporate scene features far outperform models that only depend on social interaction. We attribute the better performance of the convolution LSTM and conv LSTM models to them incorporating scene features because image data provides more information than simple X and Y coordinates over 8 timestamps. Our initial hypothesis was that the social LSTM model, with its context of agent-agent interaction, should show better performance than other models. However, we find in reality that models which incorporate scene features far outperform social LSTM. And this is because the sequence length of 8 timestamps on the forking paths dataset does not provide much scope for incorporating agent-agent interaction. Here's a visualization from our social LSTM model, which shows in red and green here the predicted and the ground truth trajectories of a single pedestrian in a scene. Key observations are that this trajectory does not intermingle with other trajectories, meaning that social interaction is successfully modeled, and that the agent does not jump abruptly from one part of the scene to another. In summary, our contributions are that we've used a new simulated dataset, the forking paths dataset, and established new baselines on this dataset. We've studied the effects of agent-agent interaction in the real world as well as simulated settings and explored novel architectures in these settings to incorporate spatiotemporal features to aid in trajectory prediction. Thus, we've laid the foundation to extend this current work for incorporating both agent-agent and spatiotemporal features in a single model. Future work could explore a social conv LSTM model, which combines the strengths of the social LSTM model and the models that exploit scene features, and also incorporation of attention, in which attention could be defined over other agents in the scene, visual features, as well as self-attention over one's own past history. These are our references. Thank you.